Okay, so we are going to be solving differential equations. We sort of started this in class already, and I'm going to give you some examples ranging from real basic to ones that have discontinuities and they get a little bit more interesting. So the first one we have here is dy dx equals negative sine of x. And as we discussed in class, when we're solving a differential equation, we're simply looking for the function y whose derivative in this case would be negative sine x. Most of you can tell probably that the antiderivative is going to simply be cosine of x. But because there are many answers, you can put a plus or minus as many constants as there is. We're going to add a plus c to represent all those constants. And what's going to happen is these constants are basically going to shift the graph up or down, creating parallel curves. And I went ahead and graphed that on my calculator to show you. So I have it here showing you y equals cosine of x plus 0. Right here, the red one, that's going to give you cosine of x minus 2. You'll see minus 1 start to come up here in a little bit. And I'll pause it while it draws the others. So you can see here that we formed a set of parallel curves that don't really touch each other because they're exactly the same, just shifted up or down. And I actually could have filled the entire screen by just continuing to add another plus 1 and another minus 1 down here. Just for your information, these parallel curves are called, they're called a family of functions. That's actually what they're called, family of functions. Have a kind of a cute name. Now, in this family of functions, if you are given a specific or an initial condition, one of these is going to satisfy it. So when you're given an initial condition, let's say that our initial condition for this particular one, for this particular example would be, let's see, pi halves comma 1. Just like we did in class, this is your x coordinate, this is your y coordinate. You're going to replace x with pi halves and you're going to replace y with 1. And then you're going to solve for c. If you recall from the unit circle, the cosine of pi halves is simply 0. So we get that 1 equals c. So your final answer for this is your general solution. For your specific solution would be y equals cosine of x plus 1. And if we go back to that family of functions, y equals cosine of x plus 1 is going to be, let's see, this is cosine right here, so it's going to be this one right here. Kind of putting it in green. But that one is a specific one. And we could just kind of ignore the rest of them, and this would be the specific one that contains our initial condition as stated. So that's an example of a family of functions. That's what they look like. So let's go back to our notes. And now we're going to do a second example. This example that we're going to work on is a little bit different because it contains a discontinuity. So let me rewrite it so you can see how this really looks. It's negative 1 over x squared. This is the differential equation, negative 1 over x squared. So what we're going to go ahead and do is we're going to take the antiderivative of this. And in order to do that, we can bring this guy upstairs. So it will be negative 1x to the negative 2. We will then add 1, which gives us negative 1, and multiply by the reciprocal, making this positive x to the negative 1, or 1 over x. Again, that's going to be plus c. Something that you're going to notice about this function is that both the differential equation and the solution have x equals 0 as a restriction, and that's going to come into play here in a little bit. Okay, so the initial condition that we're going to be using for this one is going to be 1 comma 3, and you're going to go ahead and replace x with 1 and y with 3. So we see 3 equals 1 plus c, which of course makes c equal to 2, and our answer would then be y equals 1 over x plus 2. Okay, and that's our solution. Now, this is a little bit problematic because I specified it from the beginning that The specific solution must exist in a continuous interval and contain the initial condition. Well, right now, this solution does not exist over a continuous interval. Right now, this solution exists over a discontinuity. It exists to the left of 0 and to the right of 0, but not at 0. So let me show you what the graph would look like. Okay, here's the graph of 1 over x plus 2. You're going to notice that there's a discontinuity right at x equals 0 as we predicted. So this is divided into two sections. A specific solution cannot exist when there are over two sections. It can only exist on a continuous interval. So that means we have to pick a side, either the left side of this graph or the right side of the graph, but we can't have both. The way that we pick is we utilize our initial condition. Our initial condition was the point 1, 3. 1, 3 is located on this half of the graph. So our solution is simply going to be the antiderivative that we found, the c that we found, but we have to state the domain, and we have to state the domain because we cannot have an answer over a discontinuity. In this case, we're going to pick 0 to infinity. So this is a good answer, but if you want 100% on it, you've got to be able to state the domain. In the previous problem, we had no reason to state the domain because there was no discontinuity. In this case, there's a discontinuity, you got to pick a side. And you pick the side based on the initial condition. And that is the complete solution. We're going to do another example with trigonometry. Let me set that up. Okay, so here's an example that contains trigonometry. We're going to go ahead and find the general solution by taking the antiderivative. So that'll be y equals, the antiderivative would be x squared, and the antiderivative of secant squared should be tangent of x. And of course, we need to put a plus c. For this example, we're going to use the initial condition 0, 3. So for x, we're going to utilize 0, and for y, we're going to utilize 3. So that'll be 3 equals 0 squared plus tangent of 0 plus c. As a little review, the unit circle at 0, the coordinates are 1, 0. Tangent is given by y over x. So in this case, we would have 0 over 1, which is 0. And that's how I evaluate tangent of 0 as 0. 0, of course, is 0. And 3 equals c. So our solution would be y equals x squared plus tangent of x plus 3. Now, tangent of x is defined as y over x, so you know it's going to have discontinuities anytime that x is equal to 0. And x is going to be equal to 0 at pi halves and any multiple of pi halves. So for example, 3 pi halves. And if you keep adding pi, you're going to keep getting a multiple of pi halves, or subtracting for that matter. And anytime you hit a multiple of pi halves, you're going to have a discontinuity because the x coordinate is 0 in that case. So what does that mean for us? Now I'm not going to graph the entire function, but what I am going to show you is that anytime we are at pi halves, this will be 3 pi halves. I'm going to go backwards as well, negative pi halves. Here's negative 3 pi halves. Anytime I have a multiple of pi halves, I'm going to have a discontinuity there, which means that I've got to pick an interval between these pi halves. Whoops. Okay, I can't just say that this is the answer because right now this extends over discontinuity. So I go to my initial condition and ask myself, well, where is that located? That's the point 0, 3. So that would be located right here in between these two discontinuities. So that means that my answer is not only this antiderivative and this initial condition with the initial condition that helped me find 3, but it means that I've got to state my domain as well. And in this case, my domain goes from negative pi halves to positive pi halves, because that is the interval that contains my initial condition. And that's it. So again, anytime your answer has a discontinuity, you have to pick an interval that contains the initial condition in order to get 100% of it correct. The equation is not good enough. It has to be the equation plus that domain. If there are no discontinuities in your answer, and in your derivative, then don't worry about it. No problem. You just give the equation. So let's set up one last example that involves natural log. So here we are, dy dx equals 1 over x, and the solution, by now you should recognize it as natural log of x, and then plus c. And that would be the general solution. But I'm going to finally explain the whole absolute value because, see, there's a problem between this differential equation, this derivative, and this solution. You see, the domain of this differential equation is all numbers except 0. You could have positive x values, you could have negative x values, you just can't have 0. But when it comes to natural log, its domain is from 0 to infinity. You cannot put a negative number inside a natural log. So that means that the differential equation and its solution have different domains, and that can't be true. They're supposed to match. The domains are supposed to match. Since the differential equation was given to you, this is the domain that matters. That means your answer has to match that domain. So how do we make it so that natural log will accept negative numbers when it doesn't naturally? Well, what we do is we simply put an absolute value on it. And we say, all right, if we put an absolute value, then now the domains match. You still can't plug in a 0 into a natural log, but that's okay because your differential equation did not allow it either. But you can now put in positive numbers and you can put negative numbers because once you take the absolute value, you'll be just fine. Okay? And so I'm going to go ahead and give you the initial condition for this one, and we're going to use negative 1 comma 0. And so right away you're going to see if I did not put the absolute value, I would not be allowed to put this negative 1 in here. But since I have my absolute value, I'll replace 0 for y. I'll take the natural log of the absolute value of negative 1 plus c, and the absolute value of negative 1 is simply natural log of 1, which you should recognize as 0. And we can see here that in this case c is 0. So my solution is going to be y equals natural log of the absolute value of x plus 0, or you don't have to write it. So I want to go ahead and show you on the calculator what that looks like. And I have natural log of x here. I'm going to press graph. It's going to graph it for me. Now, if I had not put that absolute value, this left half would not exist, only the right half. But as a result of putting the absolute value, it basically gives me the reflection about the y-axis because it allows me to put in both x's and y's. You still have your discontinuity at x equals 0 right here. It's still there, and that's fine. But that just means we got to pick a side now. Now, if you remember, our initial condition was negative 1 comma 0, which is located right here. So in this case, we don't want to pick the right side because it does not contain the initial condition. We want to pick the left side, which means that the solution is going to have a domain of negative infinity to 0. So this is a good answer, but it's not 100% correct unless you state the domain. And because of our initial condition, we're going to pick negative infinity to 0. Now, you didn't really have to look at the graph of these. You could just know, hey, my discontinuity is at 0. Okay, my discontinuity is at 0. You can see that from the differential equation. And I'm going to pick the side that has the initial condition, which would be negative infinity to 0. And that's pretty much it. So hopefully this made sense. Your assignment will be on Canvas, and we'll see you on Wednesday.